this seminar, we looked at each other as executive of UCBC, and that's Tyler Williamson, Karen Kopchuk, and Rob Dearden and myself, and the choice was pretty easy. And that's also because Gordon Fick, who is Mr. Biostats for the University of Calgary, is going to retire in June, and we wanted to take this opportunity to hear in a broader public from what all the things that he can present. So giving an introduction of Gordon is not that easy. He has been with the University of Calgary for quite a while, since 1996 actually, as a professor of biostatistics. He has been quite a productive researcher with lots of papers and also lots of collaborative papers with people, particularly in medicine, but also in veterinary medicine. So, but you know, it's being a researcher is one side of Gordon Fick. What actually is the side that I think is his biggest footprint is as an educator. Gordon has educated generations now of biostatisticians, of people that work with biostatistics or health researchers at the University of Calgary. Gordon started biostatistics 1, 2, 3, and a lot of other courses. So, and then he was on the committees of a lot of supervisory committees of graduate students, more than 75 graduate committees. So an enormous footprint, and we in a way don't like to see him leaving, although knowing Gordon, and I consider him a good friend, I think we will hear from Gordon in the future as well. And if it won't be on biostats, then it will be on jazz. Because Gordon is also, since 1995, a disc jockey with CJSW, the University of Calgary radio channel, where he presents from 7 to 8 p.m. on Wednesdays and has his own jazz programs. So if you really miss Gordon and you want to hear his voice and also his rich opinions, then, you know, Wednesday evening. So Gordon is going to present today on odds ratios. So Gordon, the floor is yours.
Thank you very much, Herman, and thank you to the University of Calgary Biostatistics Center for inviting me to present here on this remarkable April the 24th. Obviously, when this invitation was first given to me, the plan was that it would be a face-to-face session in G500 as usual. We're dealing with such different times, however, I have been using the Zoom facility for a while with in various contexts, and I think it works fairly well. This is joint work with Diego Nobrega, and Diego and I have been thinking about this for some time. My interest in this project actually goes back roughly even half of my career, really. And fairly recently, Diego and I have found some approaches that I think will be of interest. And so I think that I made the title of my talk rather provocative, perhaps, by including the word surprise. And some of my students will note that I'm actually using some color in my slides, and maybe something that I haven't always done. Okay, what I'd like to do is set up some of the familiar, maybe familiar fundamentals for this work first, then to describe where the challenge comes. Many of you may be familiar with this literature. I'm going to present it, though, from the point of view of the population world, rather than in the sample. the context for detailing the issues with population characteristics turns out to be, I think, the clearest way to move forward. And as my students and many of my colleagues will know, I tried to pare this down to the very simplest circumstance in which the issue appears. There's been a lot written about this topic, some of it in very complicated and elaborate settings. But I hope you will all agree that by presenting this material in a comparatively not introductory, but simple, well, apparently simple way, that maybe the issues will be fairly clear. So we're going to discuss a cohort study in which we have interest in a disease exposure relationship, and we have 2 strata. So we will have 4 stratum-specific probabilities. We'll have the stratum-specific probabilities for those in the group that are exposed, and we'll have the stratum-specific probabilities for those who are unexposed. Also, we will have a characteristic that determines the crucial issues here, and that is the fractions in the various strata. Now, the population characteristics here, the probabilities, are things that we are anticipating would be generalizable. However, these fractions that I will be discussing are things that are typically specific and to projects, and arguably represent an unknown. Now, there's 2 of them in this context and these objects, both of them are fractions, and I'll be discussing this a bit more, but they are not, in the best possible way of thinking of this, to be interpreted as probabilities. So first of all, W0, that is the proportion of the unexposed that are in strata 1. So I'll circle this with my pointer here. So it's the proportion of individuals who are unexposed in strata 1. Obviously then, 1 minus W is the proportion that are in strata 0. Similarly, we have the proportion or the fraction of individuals that are exposed in strata 1 and then those in strata 0. These characteristics are typically specific to the study and are not generalizable. And I'll speak to that more as we move forward. So we have 4 probabilities and 2 fractions. We will view them all as completely unknown in a sense. We will think of the 4 probabilities and the 2 fractions as quantities we wish to study. In the health literature, then, we have the usual rate or risk difference. We have the risk differences in the 2 strata. For example, the risk difference that's specific to strata 0, the risk difference that's specific to strata 1. We have then the risk ratios, we have the health ratios, and we have the odds ratios. It turns out that if we restrict our attention to one of these 4 types of measures of association, we get different issues, we get different things that we can see. Now, what we're going to be looking at in this presentation today is a circumstance in which there is no modification. So we're going to be looking at circumstances in which, for example, the risk difference in stratum 1 is identical to the risk difference in strata 0. That would mean that in principle, we could study the assumed common risk difference and the crude risk difference. We could do so separately again for the risk ratios, health ratios, and odds ratios. Each of them will display different features. It turns out then that it is crucial in understanding these issues to keep straight the fact that modification is specific to the measure of association and confounding is specific to the measure of association. Let's look at the first circumstance. Let's suppose that we are prepared to assume at the population level that there's no risk difference modification. That means we have the assumed common risk difference. The risk difference in strata 0 is the same as the risk difference in strata 1. Then it means we can compute these two characteristics, the weighted sum of the probabilities in the unexposed and a weighted sum of the probabilities in the exposed, where the weights are then this characteristic that I was calling the fraction that was determined by the study, but in principle then would be unknown. However, when we compare these two weighted sums, we get what is in the literature is called the crude risk difference, once we specify the fractions. A little bit of simple math shows that the crude risk difference is the assumed common risk difference times this product of the difference between the fractions and the difference between the probabilities for those unexposed. Let's look at this first difference, the probability of in strata 1 for those unexposed, the probability in strata 0 for those unexposed. That difference must be non-zero for the crude to be different from the assumed common. Further, the weights must be different. This simple formula displays the fact that in order for the crude to be different from for the assumed common, the fractions must be different and the probabilities among the unexposed must be different. Notice also, by the way, here that since we're assuming no risk difference modification, the difference between the two for the unexposed is the same as the difference for those exposed. So now we come to think about displays that are designed to illustrate these weighted characteristics. Some very simple mathematics shows that these two weighted sums differ only by the risk difference. It is indeed the vertical distance between these two lines. It is a constant vertical difference. Time for an illustration. There's a fair bit going on here, and I hope the illustration will enhance the understanding here. Let's consider some examples where the probabilities are as specified here. We can notice that for stratum 0, we're discussing a difference of 0.1 to 0.4. That means the risk difference in strata 0 is 0.3. Similarly, if we go to strata 1, we see we get a difference of 0.9 minus 0.6. Again, 0.3. That means that the risk difference displays no modification. The two stratum-specific risk differences are the same. Further, we can see that if we were to consider any linear combination for those exposed compared with the linear combinations for those unexposed, we get a constant vertical difference between the two. That means that in principle, if we had, for example, in both cases, the fraction was 1/2, we get the same difference of 0.3. However, if the weights or the fractions are different, that's where we have the potential for confounding. So we've got the probabilities for those unexposed being different, and when the weights are different, that's when we get confounding. This is very visually attractive when we have no modification. And it can be argued that that's the only time when one can meaningfully discuss confounding, in the absence of modification. Here I'm showing you a little illustration where the weights are very different and we get a reversal of the risk difference. This is a circumstance in the literature where people would say it's very clear that the strata are confounding because the crude and the assumed common have changed sign. There's a lot of literature on this topic though, not for now. Let's look at very briefly now at the circumstance where we have we have interest in studying a risk ratio. Little more complicated now. The risk ratios will be the same if there's no risk ratio modification. So that's saying the risk ratio in strata 0 is the same as the risk ratio in stratum 1. And then we'll call RR the assumed common risk ratio. Using some of the basics that I illustrated for the risk difference, we can then see that the crude risk ratio is the assumed common risk ratio when this expression is equal to 1. It turns out that that expression will equal 1 precisely in the same circumstances when this product of two differences is 0. In other words, we have the potential for modification when we're studying a risk ratio confounding issue. We have a potential for risk ratio confounding when the product of those two expressions is 0. It's not 0, excuse me. Now, what is not entirely obvious, but requires a little bit of math, is that if we were to graph those same functions on the logarithmic scale, that's P1 of W and P2 of W, again, we will see a fixed vertical distance between the log of P1 and the log of P0. That is precisely the log of the assumed common risk ratio. Another example will help. Let's suppose that we have no risk ratio modification. And further, what we're going to do is display these risk ratios on the log scale. We do so, just to confirm this, if we compare the ratio of the two probabilities in strata 0, we get 4. That's 0.04 and 0.01. The ratio is 4. If we compare that same ratio in strata 1, we see that we get 0.9 divided by 0.225. Again, the risk ratio is 4. That means, in this circumstance, that the risk ratio in strata 0 is the same as the risk ratio in strata 1. Hence, there is no risk ratio modification. But as I mentioned earlier, graphing on the vertical scale, the log of the risk ratio versus the fractions, we get two curves that have a fixed difference between them. They are parallel curves. For illustration here, I'm showing you a situation in which if there were differing weights, though, we could have, for example, if we compare the point on the red line here with a weight a little under 0.2, with the rate on the with the log risk ratio On the blue line, that is a little bit less than 0.9, what we see is the risk ratio on the log scale is 0. In other words, there are combinations of the weights in which the adjusted, or if I may, the assumed common risk ratio can be much different from 1, but the crude risk ratio is equal to 1. Now, what was documented some time ago was that this feature of these parallel curves, although written in different language with different notation, was identified for both the risk difference, where we're looking at parallel lines, and for the risk ratio, where we're looking at parallel curves on the logarithmic scale. And there's been a lot of terminology associated with this feature that's been identified in literature. Now we go to the tough part, the tougher part. What if we were to make the assumption that there is no odds ratio modification? Fairly common in the health research literature. We fit models perhaps that are additive only on the logit, with the logit link, in which we are implicitly assuming that the odds ratios, that the study of the odds ratios is not afflicted with modification. In its simplest form, we're saying that the odds ratio in strata 0 is the same as the odds ratio in strata 1. So we might be wondering, do we have the same feature of parallel curves that we saw with the risk ratio? That turns out to be false. It is not the case that the log of the odds with regard to those exposed and the log of the odds for those unexposed differ by a constant which we would have thought might be the log of the assumed common odds ratio. It was identified some time ago that that was not the case. What are the implications? It means that the vertical distance between these two curves is not constant and is in fact a function of W. So, well, okay, it's a function of W. Well, that's interesting. And further, we can then see that, well, that vertical distance between those two curves would be analogous to a crude odds ratio in certain contexts. That one would say, wait a minute, that's not the same as the assumed common odds ratio? How can that be? If the weights are the same, wouldn't we be prepared to assume that there can't be confounding? Well, it turns out that we have to be very careful how to use the language, the epidemiology here. We have to be very cautious. Let's look at a numerical example again. Let's look at an example. I'm trying to pick numbers that are as clean as possible. You can imagine, many of you will know that, okay, this is starting to get even more complicated, but let me give this a try now. Let's suppose that we think about now the log odds ratio in strata 0 and the log odds ratio in strata 1. By choosing the numbers -8 and -9, we can see that the log odds ratio is 1 in strata 0. With the numbers -1 and -2 in strata 1, we can see that the log odds ratio is again 1, the difference between -1 and -2. We're going to be graphing on the log odds ratio scale again. So we can see that here we're looking at a circumstance in which the odds ratio itself is fairly substantial, right? It's this number that's more than 2, nearly 3. And you might, if you looked at this visual, you might be thinking, there's the vertical distance, 1 unit here. Here's a vertical distance here, looks about the same. Here's a vertical distance here, it's a bit harder to see, but looks about the same, might be near 1. Well, a long time ago, I'll cite Professor John Tukey here. Tukey would say, you can't look at curves like this looking for differences by staring at them if the curves differ a lot. A long time ago, it was suggested you must look at the differences. It's analogous to looking at the actual residuals in complicated situations, rather than trying to look at the fitted values directly. So what we're going to do now is graph the vertical distance between the red, that's the exposed, and the blue, which is the unexposed. Okay. Remember, before, those differences were just the assumed common measure, the assumed common risk difference, and or the assumed common risk ratio. What do we get now? What we get is a function that is not constant. Let's look at this visual and let me see if I can help you to understand what's going on here. Here we have, with W0, the difference between the two, the red and the blue, is 1. That's the log odds ratio in strata 0. Over here, with the fraction being equal to 1, we get the log of the odds ratio is 1. In other words, we have no odds ratio modification. Both stratum-specific odds ratios are 1. However, what we can see is that this number drops below 1. Even if we were to have a study in which we had equal numbers of individuals in the strata, both exposed and unexposed, where the weight is 1/2, you can still see that the difference between the red and the blue is attenuated. It is not 1. It's 0.9. And in fact, for different common fractions, the fraction of those in strata 1 who are exposed and the fraction in strata 1 that are unexposed, we can get, for a very low weight, we can get a number that's even below 0.85. Now you might be thinking, oh, this is, what's that? Who cares, right? Is this a big deal? Does this matter? Will people be troubled by this? This attenuation issue was identified some time ago. It goes by a number of different names. And I would say that I'm not entirely clear on which one we should be using in 2020. I'm going to stick with attenuation because what we're going to be able to see in a minute here is that the crude will always be attenuated. It'll always be less than the assumed common. So there's other terms that are used. Non-collapsibility. Ooh, that's quite a mouthful. It's out there. Some authors are even referring to this phenomenon as nonlinearity. I really am not comfortable with that. Where it gets even worse is that in some literature, this issue of attenuation is sometimes thought to be confounding, and it is not. It gets even worse in some, shall we say, lesser literature when this matter is discussed with the presence of modification, in which case it's even less obvious what's going on. So it gets even worse still because there are many writers that merely offer examples of attenuation with specific sets of data. Now that's fine for illustration, but doesn't help per se if you want to understand when attenuation might matter. Then there's some very nice examples in the literature of where there's clear attenuation as soon as you specify data sets. I wanted to single out for you a remarkable individual and a remarkable paper. Her name was Myra Samuels. Dr. Samuels was a student of Jerzy Neyman. Yes, indeed. That is Neyman, the famous Jerzy Neyman, responsible for all of the important work connected with Pearson, the Neyman and Pearson work, the Neyman-Pearson lemma, Neyman's work on hypothesis testing, accept, reject terminology, all of that work. Much of that is attributable to Neyman. And while Neyman was at Berkeley, one of his students was Myra Samuels. Myra Samuels spent, I believe, almost all of her regrettably short career at Purdue University. And for the latter part of her career was actually in the Department of Veterinary Pathobiology. Nice connection here for you folks in the veterinary world. Unfortunately, Dr. Samuels died when she died at a very young age. She was only 52, died of cancer. But it turns out she has had some amazing publications. And I'm just going to cite one of them for you here that was published in 1981 in the very, very fine journal Biometrica, where some of the most crucial work in statistics has been published over the years. And in that paper, not only does she identify the attenuation issue that I am presenting here, but provides a proof in a fairly general setting for that attenuation. In Dr. Samuels' article, there's a couple of parts to it that are really quite something. Dr. Samuels is very, shall we say, flippant about the current state of the literature in her introductory remarks. I rather like that, actually. Rather critical. She used words like confusion and oversimplification. many very valuable things. But in her paper, which covers quite a bit of material, not all of it related to the topic here, quite a bit of it, quite remarkable actually. But when she gets to the crucial part where she's demonstrating attenuation, she constructs a rather intimidating looking formula that's used, in which she says, it is straightforward to show that. It is straightforward to show that. Oh yeah? And then in one sentence says, using Jensen's inequality, one can show, and I'll re-express this, one can show attenuation. Basically, it's that these odds ratios will be closer to the null than the assumed common odds ratio. So if the odds ratio is greater than 1, the assumed common odds ratio is greater than 1, then the crude odds ratio will be attenuated. It'll be closer to the null. Same thing if we had the odds ratio less than 1. Now, it's very interesting that there's a vast and shall we say troubled literature connected with this topic. But Dr. Samuels gets my high marks, makes it very clear, and provides the ingredients for proving this attenuation. Well, guess what? I took this on a while back in conversations with Diego, and I thought, okay, well, Dr. Samuels says it is straightforward to show, and then says using Jensen's inequality. Well, I spent a lot of time with this. How do I use Jensen's inequality correctly here? How do I express these expressions correctly here? For a while, I had back and forth with Diego, and we were like, oh, maybe it isn't right. Maybe this is, why wouldn't she include more of the details? Then, well, yep, it turned out, yep, she was right. And with a lot of heavy lifting, I was able to show that, in fact, the attenuation is always present. So it's an inequality statement that Dr. Samuels was able to display, that the assumed common odds ratio would be different from and larger than or further away from the null than the crude would be. Even in, just to emphasize this, even in the absence of confounding. So, as I said, then my interest was, in this particular setting, Diego and I discussed, well, it's one thing to say that there's an inequality, that one number is less than another, but what would the magnitude of this number be? Then I decided, all right, well, how about that? We have expressions, pretty complicated ones, but we have expressions for that difference. Can we find the critical points? The critical points for this function, this difference. Could I determine where the attenuation was maximum? We knew from Jensen's inequality that it would be an attenuation. But how large could that attenuation be was an interesting topic. There are some places where this, so anyhow, yeah, to give the surprise away, we're fairly sure that we have now closed form expressions for the weight where the attenuation is maximized and what that maximum value would be. This is still ongoing work with Diego and I. We're becoming increasingly secure about this result. It turns out that when will it matter? Well, this is another very demanding topic and for which there's been some discussion in the literature. It turns out the odds ratio is the risk ratio divided by the health ratio. So when the health ratio is near 1, then the attenuation won't matter very much, right? Because then the odds ratio will be essentially the same as the risk ratio where we know there's no attenuation. A little bit of simple math can show that if, for example, we take a circumstance where the health ratio will be near 1 is a circumstance in which the rates are small. Making that a little firmer, if we consider such rates, fixing the probabilities for a given, say, proportion, the risk ratios will be constant, but as the overall probabilities in the 4 cells get small, we get the health ratio being 1, and so the odds ratio will be the risk ratio. So that's a circumstance in which and this has been demonstrated in the literature, that the attenuation issue will be minor if the probabilities are small. It's when these probabilities are larger that we can see real differences. Well, here you are. This is where I guess I'm a little self-indulgent and maybe a little tentative here. But here is the formulas that we've been able to determine for where the attenuation is maximum. We're fairly sure that this result is true, but there may be some caveats and some special cases. We're still working on that. We get this odd looking expression that the weight or fraction where we get the maximum attenuation is the square root of this thing. Wow. And then we put in that weight and get the maximum attenuation. So that was sort of an interesting sidelight for us. And again, this is a topic that we're still working on and really trying to really nail down. We've looked at some examples in which things seem to be okay. Maybe still, though, needing further work here. This is, yes. Now what I wanted to do, oh yes, and here you can see in my next slide, I'm going to use the red font again for surprise, because there are definitely circumstances where the attenuation can be large. Going back to this display, you can see that, well, the attenuation is from 1 to 0.8, a little bit less than 0.85. You might say, well, practically, will that matter very much? Well, what we have done is look at various combinations of these values of the 4 probabilities and looking at the maximum attenuation with the assumption of no odds ratio modification. And just for interest here, just very briefly, I wanted to point out to you that, in fact, the attenuation can be very large. Now, these are rather rarefied examples, but the point of this is that it is not a minor issue, at least in some circumstances. So let me just walk you through this visual a bit. We have that the difference between the two, the red and the blue curve, in strata 0 is 1. That's this point here. The difference between the red and the blue curve in strata 1 is also 1. However, in between, the difference can be even almost as low as 0.1. That's a huge difference between the assumed common, which is 1, and the crude. Even when the weights are the same. Hence I promised you a surprise. Maybe you're going to be saying, well, this isn't much of a surprise, but it is. It is a statement that the magnitude of attenuation can be very substantial. Notice that we would be going from an odds ratio, assumed common in the 2 strata of almost 3, to an odds ratio that's near 1. Quite substantial, even though there's no confounding. Well, I've only got a couple more slides for you. What is also a topic that we've only begun to explore is when we move from the population domain to the sample domain. Now we're going to have sets of estimates of probabilities, and we will have then the actual fractions once we have the data at hand. What that means is that we won't have the luxury of all possible values of probabilities, all possible values of fractions, but rather we will have finite sets of them. And that's a topic that's still quite interesting. We've only really started this. Add to the mix the challenge of circumstances in which the modification may not be exactly 0. There may be minor, say, odds ratio modification, in which case we might then say we would like to look at odds ratio confounding. And the whole issue of attenuation when the odds ratio modification is non-zero is also a topic that, to my knowledge at least, has not been well explored, or explored at all, actually. So there are Also ongoing in this is a fairly large literature on whether or not we can, in this instance, with the actual data, consider counterfactuals. That's where we consider the actual data points that are available from this study. We'll have the four stratum-specific probability estimates. Then we'll have two more quantities. We'll have two more quantities that reflect points on those curves. And there is an interesting but troubled, in my opinion, literature on the merits of using counterfactuals to resolve these issues. This is a whole other topic, one we're not going to discuss here. Well, I would like to end by mentioning that we have in development scripts to display the visuals. The visuals, I think, help with understanding what's going on here. Diego has prepared a very, I think, reasonably bulletproof package in Stata, and many people, both students and colleagues, have found it of interest to try. And very recently, we've begun development of an R package. Indeed, Diego has very recently got some of this put together. So you're seeing some of this work in a still, I say, unvarnished way so far. But I hope that you'll appreciate my enthusiasm for this, and my joint work with Diego. We're very hopeful we'll be able to continue. We are hopeful, and again, this is now sounds like I guess it's kind of a promise, but we're going to have at least one publication from this. I'm convinced of it, although I've been wrong lots of the time. My filing cabinet filled with rejected papers. But nevertheless, we do anticipate one manuscript, and I think that we'll be able to it may get some attention. With that, I will close then and invite people to ask me questions. What you can do is send me your questions through the Zoom chat facility, which you should be able to access. If you would prefer to make a remark, we may be able to turn on your microphone too, if you'd like to try to do that. Again, many thanks to the University of Calgary Biostatistics Center for their invitation for us to present this work, and thank you all very, very much. We have one question here. Dr. Williamson says, excellent talk, Gordon, thank you. What would you recommend to an epidemiologist designing a new study who may not fully understand all of these issues? Well, I think there will be a paper that once we get that paper out, we'll be able to cite it. Certainly, I would say that what also I would recommend is some of the earlier work that is in two textbooks. The first one that comes to mind is the very fine book published by the veterinary group at the University of Prince Edward Island. The first author's name is Dohu, and their book has a section illustrating some of the issues that they had identified a few years ago to do with attenuation. I would say that's one resource they should at least look at. Another one would be the excellent but considerably more demanding book by Dr. Stephen Newman. His book is on, I think it says a title like Biostatistics for Epidemiologists. It is an extremely scholarly book filled with many demanding issues. And Stephen took on this issue as in one of the sections in his book. Again, I think I've had some conversations with Dr. Newman, and I think that he would acknowledge that some of that work could be now viewed as rather preliminary, but it's still a very interesting place to go. Dr. Alberto Nitelagira asks, designing a study and wanting to know your suggestions regarding the analysis of such health data. A very, very good question as well. Alberto, I would say that what we do know is if the crude is in fact larger than the assumed common, then we may still be able to say confidently that there is confounding and that we should be reporting the assumed common. Because even with the attenuation present, if in fact the difference between the weights is large enough, then we still see confounding and we cannot report the crude. Where it becomes less secure for me is in this situation where there's a crude that's less than the assumed common. And then I would say that may require a more detailed and harder study. Now, many authors, we talked about this over the years, both in my classes and other words, would say, well, maybe if you're a little bit unsure, maybe you should be reporting the assumed common anyhow. That if there's instances in which you're a little worried about this attenuation issue, then maybe it might be a good idea to report the assumed common. Or maybe even better still, sometimes you might say it might be better to report just the stratum specific estimates themselves, right? They should then in this instance one be looking at risk ratios rather than odds ratios in this instance, especially if it's a cohort study. I'll shamelessly mention my joint work with Dr. Gurbakshish Singh, in which we are attempting to provide circumstances in which health researchers can use models for risk ratios again, rather than worry about the troubles. Yeah, I wonder about Mandel and Hansel. That work of Mandel and Hansel from the 1950s, quite something. I see Karen is asking for our scripts. Certainly, I would say that Diego and I are quite comfortable with the Stata code right now, and the R package. We're both going to be putting our minds on it in the next while. Although Diego is far busier than me, I have less on my plate, and I'm not nearly as proficient with writing and programming.
Gordon, can I ask another question?
Yes, please, Herman.
So you have such a wealth of experience with biostatistical analysis and also with supervising graduate students working with health professionals and researchers. Are there any, is there any advice or that you would want to give us on our work as epidemiologists mainly, or health professionals doing epidemiological research from these years? Anything that you see occurring over again that you would say, please be careful with that? Or
thank you for your question. My own take on this is that epidemiologists generally need to ensure they have confidence in and an active collaborative relationship with a biostatistician. I think that what we're seeing in many circumstances these days is some epidemiologists who perhaps would be, if I may, don't know what they don't know. And having an effective channel of dialogue with someone who does understand the issues better. It seems to me we've drifted a little bit from this, that perhaps there's been a little too much circumstances in which epidemiologists think they can go it alone. They can just read about it in a textbook, or they can use the knowledge they gain from courses they've taken, rather than consulting with an expert in the biostatistical issues. Where I would say there's quite an epidemic in some, not all, but in some of the epidemiology literature, is where the authors confuse population and sample. It sounds elementary, but it's not. And it's one in which one can get into a lot of trouble, in my opinion. You'll notice in my presentation with Diego this afternoon, I have presented almost all of it in the population domain, and that was intentional, because understanding the implications once we go to actual studies and actual data is much harder still.
Thank you, Gordon.
Tolu is asking, as you move into retirement, what are the top 3 wisdom nuggets? Oh my. Oh no, top 3. Oh wow. Well, I think one of them is I think the first 2 I would say relate to ensuring meaningful collaboration between epidemiologists and biostatisticians. Both need to learn from each other. And it has to be done with recognizing that it's going to take a lot of time. So the first one I would say is meaningful, active collaboration. The second one would be the crucial distinction between population and sample. And I think the third one that I would say is, and this comes up with both my students and my collaborators, is that doing a decent biostatistical analysis takes a lot of time. And I think that epidemiologists need to be more understanding of the fact that, sure, they spent 2 years collecting their data, and they've done a fine job of ensuring all of the design issues and gone through all of the hoops of ensuring that the data has been collected appropriately. But to expect that analysis will be done in a hasty manner and will be done without a whole lot of careful attention, or that one can simply use a very routine approach. So I guess those are my top 3, Tom. Thank you to Alberto for bravo and mega bravo.
Okay, I think with that, thank you very much, Gordon, for an excellent seminar. I hope you will be available for all kind of questions for the next 30, 40 years. And so thank you again from everybody who has been working with you in the last 30, 40 years at the University of Calgary. Okay, with that, this is the end of the seminar.
Bye all. Thank you, Herman.
You're welcome.